Hey, B Chemistry, welcome back to Chapter 8, Part 2. We're going to talk a little bit more about bonding today, and we're going to start with some basic information that you may have heard before in chemistry or classes before that. And then we're going to get into polarity a little bit more deeply. Okay, so let's jump in. So let's talk about the difference between representative ions and transition ions. And we want to talk about how the idea of lattice energy explains why we only find specific ions of representative elements. Like, for example, why does sodium form Na plus in compounds, but why does it not ever form Na2 plus? And this all has to do with this idea of that energy diagram trade-off. So we looked at the energy diagram in a little bit more detail and how, it takes energy to take ions from their elemental state into their ion state, but then that energy is kind of won back when we take those elements. I think the chart looked something like that. So we take those elements in their ionic state then, and we bond them together. We get a lot of that energy back out. And so this idea of this transition between the elements and the ions and how that transition, especially for metals, removing that electron is going to take energy. And so this idea of lattice energy, the energy that we get out when we form the lattice, and the idea of the successive ionization energy kind of come together here. So if we look at sodium, from sodium to sodium plus, that would be ionization energy 1, the energy required to remove 1 electron. If we're going to remove 2 electrons, and that would be the second ionization energy, that's going to be a lot more energy. We saw for specific things like sodium, for example, if we start with sodium here, we have that first electron is in the outermost energy level. Once we remove that first electron, we are drawing electrons out of the inner energy levels. Then we're drawing out a core electron. This next electron that's going to be removed is going to have to be a core electron. So we're going to see a really big jump in between ionization energy 1 and ionization energy 2. And so that really big jump would have to be compensated by the lattice energy that we get out then from taking these ions and forming them together into an ionic compound. So if this lattice energy can't compensate for this huge jump in ionization energy that we see between sodium plus and sodium 2 plus, then the sodium 2 plus ion is never going to form. If you're never going to have that energy redeemed, so to speak, then the ion's not going to have any reason to form. There's going to be no driving force behind why that ionization would occur. Now we see some general trends here in terms of lattice energy. Lattice energy can compensate for the loss of about 3 electrons from most atoms. So if you look at the transition ions and those ions that form multiple charges, you really only see charges of 1, 2, and 3. There are a couple exceptions to that, like tin forms a 4 plus ion, lead forms a 4 plus ion. If you see those ions, though, the energy isn't compensated by a lattice energy formed. There's something about the structure of that metal that allows the removal of those electrons to be easier than the removal of 4 electrons from most metals. So that would not, the driving force would for that would probably not be lattice energy. Lattice energy really can only be the driving force behind the removal of 3 electrons and then the exchange of that electron when we get it back as that lattice forms. What we see with transition metals, transition to ions too, is that most transition metals are going to exchange 1, 2, or 3 electrons for that noble gas configuration. Beyond 3 electrons, it's really unusual to see that exchange occur and be supported by, in order to reach that noble gas electron configuration. Fun fact about electrons lost from shell, we have talked about the order of filling, and we've talked about how, we have to follow the off-Baugh principle order of filling, where if we build this one, the same information is on the periodic table, and we draw slashy lines through it, we see that 4s is going to fill with an electron before 3d ever does. However, when the electrons are removed, they're not removed in the opposite order. The electrons are actually removed from the shell with the highest n value first. And so, something like scandium, for example, scandium fills 1s, 2s, 2p, 3s, 3p, 4s, and then this 21st electron is going to go into the 3d shell. So the last electron goes into the 3d shell, but when scandium is ionized, the first electron doesn't come out of the 3d shell. The first electron actually comes out of the 4s shell. So that is a fun fact that might not be as logical as other patterns that we see on the periodic table. So good to know. Maybe you'll win Jeopardy with that someday. Okay, ion size. So again, here's a periodic table that we are revisiting. Periodic table trend we're going to revisit in order to set ourselves up to understand bonding and polarity a little bit more. So ion size is not quite as clean of a periodic trend as atomic sizes. Remember, atomic size left to right is going to decrease because of the number of protons. If we look at that second row in the periodic table, lithium all the way through neon, lithium has a 3+ nuclear charge. Neon has a 10+ nuclear charge. And if we look at the Z effective, it's even more dramatic. Lithium has a 1+ effective nuclear charge attracting its valence electrons. Neon actually has an 8+. And so because we are increasing in protons without actually adding any more core electrons that block those valence electrons from the nucleus, the atomic size is going to decrease left to right. Lithium's pretty big. Neon's actually pretty small comparatively. Atomic size also top to bottom is going to increase. Again, this has to do with energy levels. So like hydrogen has 1 energy level, lithium has 2, sodium has 3. And so because of those additional energy levels, the size is going to increase. But ionic size trends are not quite as clear cut, because what we see metals on one side. Oh, that was a bad stare. That was supposed to be a stare. We find metals on one side that actually lose electrons. So lithium is going to lose its 1 electron here. And we find nonmetals on the other side that are going to gain electrons. So fluorine, which is a 9+ here and has the same amount of rings as lithium, it's actually going to fill those rings up. So lithium is going to lose an entire energy level, and then fluorine is going to fill their energy level up. So lithium when it ionizes is actually going to get smaller. Fluorine, when it ionizes, is actually going to get kind of bigger. It doesn't add any protons, so that doesn't help it shrink. It doesn't add any energy levels, that won't help it grow, but it does add electrons to its inner energy level. So if we compare fluorine with the fluorine ion, atomic fluorine, with the fluorine ion is actually going to be bigger than the atom of fluorine. And so what we see is this change. If we look at, let's say, let's do aluminum and silicone, for example, okay? In the atoms, aluminum is going to be bigger than silicon because aluminum has less protons, silicon has more protons, it's going to make it smaller, right? But aluminum as an ion is going to lose 3 electrons and get a lot smaller. Silicon as an ion, if it forms an ion, let's say it gains 4 electrons and it makes it a lot bigger. So now the atom or the ion of aluminum is a lot smaller than the ion of silicon. So we do still see these trends, like left to right in the cations will decrease, left to right in the anions will decrease, but anion versus cation, the trend's actually going to flip because of the metals losing that outermost energy level, the nonmetals filling that outermost energy level. Okay, so why do we care about the size of the ion? Well, the size of the ion affects bonding greatly. It affects stability. It determines lattice energy, the way ions are packed into a solid. It governs properties of ions in aqueous solutions. The size of the ion is going to depend on those factors we just talked about: nuclear charge, number of electrons, orbitals that are filled or emptied in the outer shell. And the size of the ion can actually give a little bit of a special bonding energy. For ions that are really, really, really small, like fluorine, oxygen, and nitrogen, they can get exceptionally close to the other nucleus that they're trying to bond with, and they can form almost like a super bond. It's a really strong bond. And we already saw this a little bit in that trend we talked about in the last video with the acids. This is another good example of what we're talking about. This fluorine ion is so small and so highly electronegative, it can get really, really close to hydrogen and form an exceptionally strong bond that will actually break the trend of the halogens group, right? All the halide, something like that, acids, the acids that form between a hydrogen and a halogen, they're all going to be super strong acids except for hydrogen fluoride. It bucks the trend because the size of that fluorine ion is so small. It can really approach hydrogen very closely and form this like super bond. So ion size makes a difference. That is one factor to pay attention to. This was the size of the ion trend we just talked about. We just looked at that. Normally metals would be bigger than nonmetals, but because metals lose that outermost energy level, the ion is actually going to get smaller. Cations will be smaller than the parent atom. Anions will be bigger than the parent atom. So we'll get this like split in the trend in that periodic trend. Okay. When ions form, they lose or gain electrons in order to form what kind of configuration? Whose configuration do they lose or gain electrons in order to match? And if you said noble gas, you are right. So we have this term called isoelectric down here at the bottom. We say that ions are isoelectric to noble gases. Iso means same, and electric is referring to like the electronic structure. So ions form in order to be isoelectric with a noble gas. For example, if we look at oxygen, fluorine, sodium, magnesium, and aluminum. Let me erase this page so you can see these a little bit better. Okay. Oxygen, fluorine, sodium, magnesium, and aluminum. Oxygen, fluorine, sodium, magnesium, aluminum. All right, so sodium, magnesium, and aluminum are all going to lose electrons. So sodium has 11, magnesium has 12, aluminum has 13. How many electrons will they have once they have lost electrons and formed cations? Well, sodium will lose 1, magnesium will lose 2, aluminum will lose 3, and they'll all end up with 10 electrons. Okay, let's go the other direction. Oxygen and fluorine. Oxygen has 8 electrons, fluorine has 9. How many will they end up with when they gain electrons to fill that outermost ring? Oxygen will gain 2, fluorine will gain 1, and they'll both end up with 10 electrons, just like neon. So ions are going to form in order to be isoelectric with noble gases. Ions on either side of neon are going to gain electrons or lose electrons until they have the exact same number of electrons as neon. We call this isoelectric. These things are isoelectric with neon because they all have 10 electrons. All right, covalent bonding. Let's switch gears here and talk about covalent bonding. All right, what kind of properties do covalent bonds have? So ionic compounds have very specific properties about them. Ionic compounds are all solids. They're all very brittle, which means if you hit them with a hammer, they shatter. They all have very high melting points, so they tend to be found as solids. They're really only going to melt in a volcano. They're crystalline. We have a whole section in our chapter that describes the structure of ionic compounds. They can be cleaved, which means when they're hit with a hammer and that pattern of negatives and positives gets disturbed. So if we hit this side with a hammer and we get this shift in charges because they were hit down, okay, we now have charges that line up with each other, and we're going to get this clean break. That's why if you ever like hit a rock and it breaks, you're going to get this really clean break. And that flat face that occurs, we say that the rock has been cleaved. And then it leaves that super smooth surface. Ionic is very driven by properties of electrostatic force. So ionic compounds form in very consistent ways. This is not true for covalent compounds. Covalent compounds are kind of all over the map. Some of them are gases, like O2. Some of them are liquids, like H2O. Some of them are solids, like diamond. Some have low melting points, like oxygen. In fact, many have low melting points. Many of them are not solids at room temperature, but some of them have extremely high melting points. So we see it's a little bit more variable. If we find a solid form in covalent compounds, there's a really good chance that it could be pliable. It could be moldable. Some of them are, some of them are not. Again, diamond or silicon dioxide are good examples of things that are not pliable. This is like quartz rock, for example. They're really driven by properties of sharing electrons. So again, forming that octet is going to be your driving factor with covalent compounds. electrostatic forces being attracted to each other, that's really going to be your driving force with ionic compounds. All right, when we look at electrostatic interactions, so electrostatic interactions, when you hear that, you should be reading ionic compounds. The electrostatic interactions that we see are kind of actually a little bit complicated. Ignore the arrows on here. If we have a hydrogen-hydrogen bond that's occurring, we have protons from hydrogen 1 and electrons from hydrogen 1. We have protons in the nucleus of hydrogen 2. We have electrons in the nucleus of hydrogen 2. And we have a lot of interactions that are going on. For example, the protons are going to repel each other. They don't want to be by each other. Same thing with the electrons. The electrons are also going to repel each other. When they get brought too close, they're going to push against each other. The protons of one are going to be attracted to the electrons of the other. And that goes both ways. The protons of one hydrogen are going to be attracted to their own electrons. So we have this complicated array of repulsion and attraction happening here. But if a bond forms, overall, the interactions are going to be attractive. But it's really not a simple case of like positive, negative, attraction, boom, right? It's this complicated array of forces that are pushing, forces that are pulling. And because of that, we end up with very specific ideal distances. When the repulsions can be minimized and the attractions can be maximized, then we get this perfect distance of attraction. We get this low potential energy. If you have too much repulsion, you're going to have a high potential energy system that's going to tend to break apart. If you have too much attraction, you're going to get this potential system that's going to collapse in on itself, right? If you're too far away, then the attraction isn't as maximized as it could be. You're also going to have this high potential energy system. And so you have to find this beautiful balance of this perfect distance. And that is where your lowest potential energy is going to be for this electrostatic bond. When you're predicting covalent compounds, on the other hand, you're not just looking at a positive-negative interaction. What you're looking at is this balance of electrons coming together, being shared, and satisfying the octet of both atoms. Or in the case of hydrogen, you're going to satisfy a duet for both atoms. And so it's not as simplified as our system that we were just talking about, even though we were just talking about how that system's not very simple either. This one's a lot more complicated because you are being driven forward by forces of like this octet rule, of this balance, of this like, I don't know, happy idea of the protons of one still being attracted to the electrons of another, but also satisfying this special stability that we achieve when we fill an energy level. In Lewis structures, since this is a model that we've created in order to represent an idea, there's a little bit of interpretation that goes along with it. Again, if you see a stick like this, a stick is going to be equal to 2 electrons that are causing the force of attraction to be completed, basically. So that stick represents a bond, but what that bond actually is 2 actual electrons. We just get sick of writing dots over and over and over and over again, and so we eventually just merge into writing sticks. We call those bonding electrons. So if you see a stick, it's a pair of bonding electrons. If you see dots, that is a pair of non-bonding electrons. And the pair of non-bonding electrons we're going to call a lone pair. So if you hear this term lone pair, it's talking about electrons that are involved. They are valence electrons, but they're not involved in the actual bond. It is possible to end up with a rogue electron that is not paired. It's really unusual. It's going to form a super high potential energy system. The system is not going to last very long. It's going to bond with something real fast, but you can actually have a rogue electron all by itself. Just very unusual. All right, so when we talk about this covalent bond, the driving idea, the driving principle here is that you want to form that octet, right? So if you have something in the 4A column or the 4A family, that 4A family comes with 4 unpaired electrons, it's going to tend to form 4 bonds. And we see this with carbon. No matter what carbon bonds with and in what ways they bond, carbon usually ends up with 4 bonds around it. Even something like carbon dioxide, in which carbon forms double bonds, if you count the bonds that formed, 1, 2, 3, 4, you still usually end up with 4 bonds. Again, this is just a general trend you see that might help you predict Lewis structures that occur. It's not always, and forever true, but it's usually true most of the time. 5, in a similar way, 5A, the 5A family, like nitrogen, it has 3 unpaired electrons. It has this lone pair of electrons at the top. And so nitrogen is going to tend to form 3 bonds. Oxygen has 2 unpaired electrons. It's going to tend to form 2 bonds. Fluorine has 1 unpaired electron. It's typically going to form 1 bond. So again, not always true, but it can provide a couple hints if you're really stuck with a Lewis dot structure as to what direction you should go. Okay, multiple bonds are possible. Multiple bonds can be found all over the place, especially in organic compounds. We see multiple bonds a lot. If you have 1 pair of electrons in between 2 atoms, it's going to tend to be it will be a single bond. If you see a double bond like this that we see in between these oxygen atoms, that's actually a double bond. And what that is 4 total electrons. It's 2 pairs of electrons. So each of these lines represents 2 electrons. So how many electrons total are you going to find in a triple bond? And if you said 6, you are right. So 6 electrons total in that triple bond, 3 pairs of electrons. Now, as we increase in bonds, so single bond versus double bond versus triple bond, the bond tends to get stronger and the bond length is going to get shorter. So single bonds are the longest, double bonds are shorter, triple bonds are even shorter yet. And once we start looking at molecular orbitals, so right now we're looking at atomic orbitals, right? SPDF, those describe atomic orbitals. Well, soon here we're going to look at molecular orbitals. And once we look at molecular orbitals, you're going to see why adding these additional bonds makes things stronger and makes things shorter. But for now, just trust me, multiple bonds are going to tend to make things stronger and tend to make things shorter. You can see that with nitrogen down here. When a nitrogen-nitrogen single bond is formed, it tends to be 1.47 angstroms. A double bond would be 1.24 angstroms, and a triple bond between two nitrogens would be 1.10 angstroms. So it's getting shorter, it's also getting stronger. Fun fact, do you guys remember what 1 angstrom is equal to in meters? It's 10 to the negative 10th. 1 times 10 to the negative 10th meters is equal to 1 angstrom. It's a good reminder. Okay, so now we get into looking at bond polarity. So we've briefly looked at ionic bonds. We briefly looked at covalent bonds. So now covalent bonds have this subset where covalent bonds can be polar covalent or non-polar covalent. So let's look a little bit more deeply in this. We talked about this a little bit in chapter 4. We want to look at this again. And then we're going to take it a little bit further in chapter 10. Chapter 10 is almost based entirely on polar compounds. Okay, so bond polarity happens when electron pairs are not shared equally. So before we get into this, notice this is talking about bond polarity. There's a second type of polarity called molecular polarity, which we will look at. Okay, so we're going to look at bond polarity right now. Bond polarity is going to help us understand molecular polarity, but you really have to make a distinction between the two. Do not get those two confused. Okay, so bond polarity is talking about the bond itself. If you look at the bond between two chlorine atoms, these electrons that are in the middle are perfectly shared between them. Chlorine and chlorine have the exact same electronegativity. These two electrons that exist between them are not going to they have no reason to be pulled one way or be pulled the other way. There's just no reason for them to be there. Same number of protons, same number of electrons, same electronegativity. They're going to be shared perfectly equally. So that would be a non-polar covalent compound. Most covalent compounds, however, are not shared equally. Most of them have some degree of shift that occurs in that bond. We can contrast that to an ionic compound, which is not a covalent compound, but provides a good contrast. So if we look at the electron in between the sodium chlorine bond, remember there's one electron that comes from sodium and one electron that comes from chlorine. Well, those electrons are definitely not shared equally. They actually get taken by chlorine and they get removed from sodium. And so it's the opposite of the chlorine element, the chlorine molecule. Chlorine molecule perfectly shares them. Sodium chloride, chlorine perfectly takes them away from sodium. And it's because of electronegativity differences. If we look at a chart of electronegativity differences, wait for it. Let's look at this one. See if it'll get big for us. There we go. Okay, so if we look at these differences, look at chlorine. Chlorine is a 3. Okay, so in a chlorine-chlorine bond, you have a pull of 3 on both of those electrons. They're not going to move. They're going to be shared equally. But if we look at the chlorine-sodium bond, chlorine is a 3, sodium is a 0.9. So 3 and 0.9, that's a difference of 2.1. It's a pretty big difference in electronegativity. Chlorine is going to have a really strong pull compared to sodium, and it's going to just take those electrons. Most covalent compounds fall somewhere in here. Now, polar bonds is going to be a sliding scale. Okay, it could be a difference of 0.4. It could be a difference of 0.8. It could be a difference of 1.9. Okay, so there's a sliding scale in here of polar molecules. Not all polar bonds are created equally, right? It all comes down to a difference in electronegativity. And that's what's going to determine the bond polarity. So if they're shared equally, it's because they're being shared between two identical atoms. Most things are going to be in the middle somewhere. And so we get these dividing categories. We have our nonpolar covalent bond. We have our polar covalent bond, which is most of them. And then we have ionic compounds on this end. And again, it all comes down to the magic of electronegativity. There are actual cutoffs. If the difference is 0, it's going to be a non-polar covalent bond. I think it's something like 0.4 or 0.3 to 2.8-ish is going to be a polar covalent bond. And then anything that's like 3 or greater is going to be an ionic compound. So there are actual like definitions. There are actual cutoff points. You can look them up. It's not super important that you have these numbers memorized. You may have them memorized still from chemistry, actually. But they sometimes, even if you look at the industry, these things overlap. So sometimes things will, polar covalent and covalent bonds will overlap and they'll get named as an ionic compound. Sometimes they'll get named as a covalent compound. Compounds of silicon are actually really common to kind of fall in the middle. Silicon's a metalloid, so it's not clearly a metal, and it's also not clearly a nonmetal. And so it kind of depends on the industry. Certain industries will classify it different ways, just depending on what's convenient for them, and they'll also name it different ways. Okay, so when this bond is not shared equally, it results in what's called a dipole moment. So a dipole moment is kind of the shift. It represents the shift that occurs. So we represent a dipole moment with an arrow. You can see my arrow down here. And the arrow points towards the partially negative side. The arrow points towards and then the opposite of that is this like plus side end that points to the partially positive side. Just a reminder that this symbol means partially. So a polar molecule doesn't have a complete charge, it has a partial charge. Since fluorine is more electronegative, electrons are going to shift toward it, and it is going to have a partial negative charge. Hydrogen, because it's less electronegative, the electrons are going to shift away from it, leaving it with a partially positive charge. So that's called a dipole moment. And if I draw something like water, you should be able to look at water and draw the dipole moments that occur from the bonds. Why don't you pause this video right now and try that with water? And so you have to decide what's more electronegative, hydrogen or oxygen. Oxygen's going to be the more electronegative one. And so our dipole moments are going to point towards oxygen with a plus over hydrogen on both sides. Hydrogen's going to be partially positive. Oxygen's going to be partially negative. Now, oxygen's not actually shaped like that, but for the sake of discussion, you get the idea. This is important because polar molecules are going to line each other to other polar molecules. So if you put HF into water, we could decide on their dipoles. Water's actually shaped more like that. and we can line HF up with water. So here's our partially negative, partially positive side. HF would line up, water's partially negative. HF would line up like this. HF, the F is partially negative. It's going to be attracted to hydrogen, which is partially positive. Here, I'll do it in a different color. And then our partially positive hydrogen here is going to be attracted to oxygen, which is partially negative. We can also have the molecules attracted to themselves. We could put water molecules in with other water molecules, and they would line up something like this, with the hydrogen of one being attracted to the oxygen of the other. Okay, so if you are given a molecule, you should be able to think about the electronegativity and draw dipole moments over the bonds. Dipole moments can actually be measured. There is an equation. You don't have to know that. You will be happy to know. But dipole moments can actually be quantitatively measured for different molecules, and their strength can be ranked. If they're measured, let's see if I have the symbol on the other next slide. Yes. They're measured in this unit. It's called a debye. It's represented by a capital D, and that's the measurement. That's the unit that they use to calculate the measurement of. Notice that it's a combination of charge and distance. So just like Coulomb's law, which is a combination of charge and distance, so is a dipole moment. If it has to extend over a really large area, it's going to be weaker. If it extends over a shorter area, it's going to be stronger, and the charge makes a difference too. If the charge is a 2+, it's going to have a stronger dipole moment. If it has a 1+, it's going to have a weaker dipole moment. So it can be measured. We're not going to deal with the measurements at all, but you should be able to talk about these factors and tell me how it's going to affect the dipole moment. All right, so here we are at bond types and nomenclature. So this is going to be a review of what we talked about in chemistry. I'm actually going to stop the video here. This is a good stopping point, and we can pick it up with nomenclature later. A good thing to do between today's class and the next class would be to try to write out naming systems from memory. Do you remember what the naming system is for ions? How about ionic compounds? How about covalent compounds? How about acids? How about bases? How about organic compounds? We have a lot of these. It would be a good thing for you to do to sit and try to write out the naming systems for all of these. And then we can plug holes and start it instead of just starting from scratch. So again, super theoretical, super abstract chapter. Way to stay with me through all of those details. Let me know if you have questions. We'll do a little bit of practice in class, but again, there's just not a lot to practice. So if you can bring questions into class that we can deal with, that's going to be a much more effective way. So let me know if you have questions. I'll see you in class.